So, as I mentioned a minute ago, we'll denote the Sharpe ratio by phi of RT. Now notice, we did not conclude that the Sharpe ratio is independent of the interest rate R, nor is it independent of the time at which we're doing the calculation. We simply concluded that it must be independent of the maturity of the bond. So we'll use the expression that the Sharpe ratio must be equal to phi of RT for some as yet unspecified function. This is a sign difference from the book. In the book, there's an error related to this part of the development I want to bring your attention to. The Sharpe ratio phi should, in fact, have a negative in the Q, and this will have, as a consequence, a sign change in the partial differential equation we will now get. So now, this is an equation, and we actually have formulas for alpha and Q from earlier, and if we insert those formulas for alpha and Q, we're going to get a differential equation that the price function P must satisfy. And the differential equation is this. Now notice that relative to the book has a plus here. It should have a minus. The plus in the book is related to the omission of the negative in the definition of the Sharpe ratio. So we should have a negative here, and namely that the differential equation of the price function P involves the second derivative of P with respect to R, the first derivative of P, and the derivative of P with respect to time. Now, if we look at this, and of course R is the short rate, and we're assuming that R follows that R process we had a moment ago. Now, it's worth pausing a minute to look at this and say there are parts of this equation that look very similar to the Black-Scholes equation. Namely, the Black-Scholes equation started with a process for S and gave an equation that every derivative must satisfy. Every derivative security, every option. Here, we started with an equation, a process for R, and developed a differential equation that every function of R must satisfy. So it's quite parallel. A process for S, a differential equation for that every function of S must satisfy. Here we have a process for R and a differential equation that every function of R must satisfy. So it's natural to compare and think, what's going on here besides that notational difference? Well, if we just shift the notation from the Black-Scholes formulas to the R formulas, we'll see that this term looks just like Black-Scholes, accounting for notation. This term looks just like Black-Scholes, except for notation. If there's a surprise in this equation relative to Black-Scholes, it's the coefficient of the R derivative with respect to P. It's this term. And I want to investigate that and explain why it is that all the rest of this differential equation looks just like Black-Scholes once we adjust for notation, which we're now going to do, but this particular coefficient is different than what's in Black-Scholes, and it's understandable why it's different. And we're going to now pursue this question.